It's okay. We are now recording. Um, if there are no questions on what we've done so far or anything else, then we will proceed with class as scheduled. Um, just a little bit of looking ahead. We're in chapter 7, 7.2. Hopefully we'll get into 7.3 today. 7 is a long chapter, and we're going to cover just about everything in it, I think. I've got to check again they came out with a new course description, and I can't recall if they included moments, center of mass, and centroids at 7.6 or 7.7, which I believe was fluid pressures and fluid forces, which I thought was a pretty important thing, but I'm pretty sure they excluded those. And since we are running sort of behind, we may not do those last two sections, but we'll see. Okay, but right now we're in 7.2 and moving along there. So no questions, issues, or concerns. Now, just a little bit of review. Last time we talked about finding the volume. The title. Okay, Chapter 7 is applications of integration. 7.1 was finding the area between two curves, basically, and some other things. 7.2 is finding mostly volumes. 7.1 was I'm sorry, said that backwards. 7.1, I said already, was the area between two curves, and 7.2 is finding volumes. The first way we did was called the disk method. Okay, what you have there, and this is a volume of rotation. So you have some curve, okay, that's revolved around some axis, or some curve this way revolved around the vertical axis. So some curve revolved around the horizontal axis or around the vertical axis. Okay, we split that into dy's if it was vertical, or dx's if it was a horizontal, and every one of those disks then was the area of the disk, pi r squared, where r was the distance from the axis of rotation to the curve. That was the radius, and that's going around here. The area of that disk was pi r squared, and then the thickness was dx, or dy if you're going that way, and that was how we found the volume of rotation using the disk method. The washer method is very similar. It's sort of like what we did in section 7.1. We first started talking about the area under a curve, which we had done before too, and then we did the area between two curves. Okay, and it was a fairly simple transition to that. It's just the rectangles then were the point on this curve minus the point on that curve. That was the length of the rectangle, then times the area. The washer method is very similar to that, if I could get it to advance. Okay, all right. The disk method can be extended to cover solids of revolution with holes in them, okay, by replacing the representative disk with a representative washer. Now, of course, if you've dealt with anything, a disk is basically kind of like this. A washer has a hole in the middle. Okay, that's why they call it that. It's not washing your clothes or washing your face, or something. It's not that kind of washer. Okay, it's a one you would use on a bolt or something like that. The washer is formed by revolving a rectangle around an axis. So here we have this rectangle. This rectangle has a length here. Okay, the length of this rectangle is the upper dimension minus the lower dimension, capital R minus little r. Okay, the width of that rectangle, of course, is W. And if you're rotating that around this axis of revolution, then you wind up with a washer. The rectangle goes around here, and the axis of revolution is there, and you have that's how we form the washer. Okay. Now, if little r, that's the inner radius, and capital R, the outer radius, okay, respectively, okay, W is the width, so the volume then would be the volume of that washer that we have right here, okay, would then be pi times capital R squared, and then if you did times W, that would give you the original disk. But then you're going to subtract that from that pi little r squared, which is where the woozle wasn't. That's the disk that's not there, okay? So if you do the outer disk thing, rectangular radius around there, pi r squared w, like we did before, minus pi little r squared w, you get the volume of the washer. And that's what they've done here and just shortened it to be pi times the difference of the outer radius squared minus the inner radius squared times your thickness of the washer, W. Now, to see how that concept can be used to find the volume of a solid revolution, let's consider a region bounded by the outer radius r of x, that's the one up here, and the inner radius r of x here. Now, I hope you're seeing that's one function up there. Here's another function down here. Okay, so if you take this little rectangle and revolve it around this axis of revolution, then you form the washers. The washer will be very skinny right here, very skinny up here, and a little bit fatter right in here. So this truly does look like a Christmas tree stand or something like that. Okay, it's a solid of revolution, but with a hole in the middle of it. Okay, and that hole is not a linear hole, you might say. It's a curved hole. Okay, and that'll still give you your volume of that revolution. Okay, so if the region is revolved around the axis of revolution, then the volume of a resulting solid is, the volume is pi, because it's pi r squared, so the pi is on the outside, times the integral from a to b, that would be the limits of your integration here. This is where they cross here, this is where they cross there, or arbitrarily given whatever, that's the a to b, okay? And then your outer radius squared minus the inner radius squared, that's going to give you the volume of the big disk minus the volume of the small disk with the pi in front of it, and both of those, times your dx, that's the thickness of the disk, which is now a washer. Note that the integral involving the inner radius represents the volume of the whole, and that's subtracted from the integral of the outer radius, which would have been the volume of the bigger disk if the hole hadn't been there. Okay, so you do the volume of the outer disk minus the volume of the inner disk, which makes the hole. Okay, so here's example 3, bottom of page 457. All right, find the volume of the solid generated by revolving the region bounded by the graphs of y is equal to the square root of x, that's this upper curve here, and y is equal to x squared. Here's the lower curve here, that's part of a parabola. This is part of the square root function. And I think we know that already, that they intersect at 0, 0, of course, when x is equal to 0, y 0. When x is equal to 0, that y 0. They also intersect at 1, 1, because the square root of 1 is 1, and 1 squared is 1. So these are the limits for your integration. Now, you could have done a dy's here, but then you would have had to change your functions, okay? And they wouldn't have been that hard to change, but you could have done it. But since they were given to you, y is a function of x, let's use a dx. So the dx is the width of that rectangle, okay, which will ultimately be our washer, okay? And the outer rectangle would be the capital R square root of x, the inner rectangle x squared. That's the radius of the inner rectangle, because you're revolving it around the x-axis, so you're just going from here. So this would be that r squared. Well, square root of x squared is just x, minus this r squared. Well, that's going to be x to the fourth, because if you square the little r, you get x to the fourth. So it'll be x minus x to the fourth dx. Pi is out in front and the dx. So that's what our the volume of revolution around the x-axis will be. Now, and I said something wrong before. Since we're doing a volume, you couldn't have gone around the y-axis. That would have been a totally different volume. Actually, it would have been completely symmetric to this, so it would have been the same volume, but that's just because these are basically symmetric equations to each other, though we don't usually talk about them that way. Okay, so this is what we've got. Now, I don't know what shape that is. It certainly is a parabolic shape this way, but the inner part is a cusp of some nature, like a Hershey's Kiss. Okay, thinking it back into that. Okay, so let's see what our equations will be. You see that the outer and inner radius, the outer radius is square root of x, the inner radius is x squared, and your formula is integrating between 0 and 1, because those are the limits of the integral. Pi on the outside, because that's for that disk minus that disk. Pi is there, pi r squared minus pi r squared. Integral from a to b of the capital R squared minus the little r squared dx, and this will be pi times the integral from 0 to 1, 0a, 1 to b, square root of x squared minus x squared squared dx. And of course that comes out being what I've already said, pi times the integral from 0 to 1 of x minus x to the fourth. That I think we can handle, right? Okay. What is the antiderivative of x? Please say you know it.
X squared over 2.
Perfect. X squared over 2 minus antiderivative of x to the fourth. Same. X to the fifth over 5. Perfect. And you're going to evaluate that from 0 to 1, which are two of the easiest numbers to evaluate. And that will be pi times, when you put a 1 in there, you get a 1/2 minus a 1/5. Put a 0 in there, you get nothing and nothing. Okay, so that's what you got. To get that on the least common denominators, that would be 10. That would be 5/10 minus 2/10. That would be 3/10 pi. That looks like to me what the volume will be. Fairly small number, right around 1, but it's, remember, had quite a gash in the middle where you subtracted that off. So let's see what they got. They did pi times x squared over 2 minus x fifth over 5 from 0 to 1, just like we did, and that gave them 3/10 pi, just like we got. Now notice they put 3 pi over 10, which is exactly the same answer. And here's where I usually get on my little hobby horse, okay, and say, if you had given this answer in WebAssign, the odds are they would have counted it wrong. Because if they were looking for that answer, this answer is not exactly the same as that one, so they would have said that's a wrong answer, when in fact it would have been a perfectly correct answer. Just as correct as this one is. There's no preference one or the other, just whether you want to write the coefficient times pi or write the numerator over the denominator. Doesn't matter. Okay? Now, evidently they're going to skip some examples here. No, not necessarily. This is the top of page 458. In each example so far, the axis of revolution has been horizontal, and you have integrated with respect to x. And I guess that's right. Okay? In example 4, which is coming up, the axis of revolution is vertical, and you'll integrate then with dy's. Okay? In this example, you need two separate integrals to compute the volume. That's because of it's not all your the ones that you do vertical, just this happens to be one that you will. Okay, so here's what you have. Example 4, find the volume of the solid formed by revolving the region bounded by the graphs of y is equal to x squared plus 1. That's a parabola that's been moved vertical translation upward by 1. Okay, so there it is. Y is equal to 0. That's your x-axis down here. X equals 0. That's the y-axis here. And x equal 1. That's the limit out here. Okay, about the y-axis. So the revolution is going around the y-axis. Okay. Now, the reason you need two integrals is down here, that's going to give you a disk. Up here, you're going to have a washer. Okay? So you'll need the disk method down here. There is only one r that matters. Up here, you're going to have a washer method because here you have an outer and an inner. Okay? Your outer is just going to be the number 1. Okay? Your inner is going to be the function here. But they gave you this function as y as a function of x because you're going to need to be doing dy's here. You need to get this x as a function of y. So let's do that first. So what we're going to do is subtract 1 from both sides to solve for x, and that would give us y minus 1 is equal to x squared. Okay? Now, take a square root of both sides, and technically you should say x is equal to plus or minus the square root of y minus 1. But you're here in the first quadrant only, so you don't need the minus sign. It's just, in fact, you don't need the plus or minus. It's just x is equal to square root of y minus 1. Now, for my purposes, I'd rather write this as y minus 1 to the 1/2 power. That will be far easier to deal with once we're doing our integration. Okay? Well, not really. No, either one of them would be fine. I was thinking something else. Okay, so now that we've got that, we can do it. We do need to do our dy's here because we don't know how to do a revolution around a vertical axis unless you do your dy's. Next section, we'll have that, but not in this section. Okay, so let's first just do the washer down here. This is going to be, this is a right circular cylinder of radius 1 and height 1. And the volume of that is going to be V is equal to pi r squared h. I really probably should put a capital R here. I will, because that's what they use, because that's all you got. And the radius is 1, the height is 1, so this is going to be pi. That's all, because the r squared here is 1, the h here is 1. So that's going to be pi. They probably want you to do the integral for it. You could if you wanted to, but man, you know that. You recognize that. There's no reason to do the integration if you know what that is. Now, the part up here though, that's going to be something a little different. Okay? If I can find, there it is, that part up here. That you will need your washer method there, and I'll call this V1 here. and V2 is the part here. This is V1 here, V2 down up here. This will be pi, I'm sorry, the integral. Now you're doing dy's now, so y is going from 1 to 2. Okay? And your outer radius is again just 1, right? The r here is 1, just like it was down here, minus, and by the way, that's 1 squared. I'll write it as 1 squared, minus, and the inner radius is going to be this one. Okay, so here's your capital R1. Your inner radius is that. When you square that, you just get y minus 1. Now watch out for those minus signs. They're there to trip you up. And then dy is the thickness of that disc, washer, whatever you want to call it. Now when you do this, you get 1 minus y plus 1. So that actually becomes pi times the integral from 1 to 2 of 2 minus y, right? Because you have 1 minus a minus 1, which is plus 1. 1 plus 1 is 2, high level math today, minus y, dy. Okay? Now you give me that one. What's the antiderivative of 2 when you're integrating with respect to y? Anybody? 2y minus
y squared over 2.
My y squared over 2, evaluated from 1 to 2. Y's are going from that. So this is pi times, when you plug in the 2, this will be a 4, minus 2 squared is 4 over 2 is 2. Now then plug in the 1, but you're going to be subtracting, so that's going to be a minus 2, because 2 times 1 is that. But then minus a minus is going to be a plus 1/2. Now, 4 minus 2 minus 2, that's just going to be 0, okay? And you have 1/2 pi left over, so you had V2 is half a pi, V1 is a full pi, so what you have, your total volume is going to be 3/2 pi. Okay? Let's see how the book did. Oh my goodness, they got it right. Again, they wrote it as 3 pi over 2, which is perfectly fine. Nothing wrong with writing it that way. I just don't usually think of it that way. I'm having trouble talking. Hold on. I think it's mostly the change of weather. I'm just very congested. And I'm having a hard time breathing and therefore a hard time talking. That's what they got. Let's watch how they did it. Okay? For the region shown in figure 721, that's the one we just had, this one right here, 721. The outer radius is simply R, capital R is 1. Okay. There is, however, no convenient formula that represents the inner radius. It's a piecewise defined function. 0 from 0 to 1, and we'll do that. Sorry, I can hardly breathe. When y is between 0 and 1, the inner radius is 0. That's what I was saying. But when it's between 1 and 2, the r is determined by this equation. But we need this equation because, you see, y is a vertical thing. Your radius is a horizontal thing. So we need to get this in terms of x. Okay? And we did this. You subtract 1 from both sides and then take a square root. And because you're in the first quadrant, I can't breathe. You don't need the plus or minus, you just need the positive. So that's where they get little r then is square root of y minus 1 for that upper part. Okay, so this is how they write it as a piecewise defined function. 0 from 0 to 1 and square root of y minus 1 from 1 to 2. It's interesting they wrote it this way, and you'll note this is okay because they are the same values. It's 0 when it's equal to 1 here. When y is equal to 1 here, that's still a 0. So they can put less than or equal to in both places because they have the same value. If, however, that had been a discontinuous function, one end would work and one end would not. So then you would have just a less than sign in one of those two places and less than or equal to in the other place. Here, we could put them in both places because they have the same value. That's sort of a minor point, but it is a point. And that's between 1 and 2. Okay? So, you have two volumes, and this seems sort of ridiculous to do this, but they did it. They're doing pi times 1 squared dy, that's pi times 1. 1 minus 0 squared is 1. So that would be y, integral of y from 0 to 1, which would be 1. Okay, so 1 pi. So that comes out being pi. No problem there. This one over here, it's the outer radius, again 1, minus the inner 1 squared, actually, minus the inner radius, which is y minus 1 squared. Okay, but of course the square root of y minus 1 squared, the square of a square root just gives you y minus 1. Okay, but when you have the minus in front, that'd be a minus y plus 1. Watch those minus signs. And 1 plus 1 is 2 minus y. So that's how you get this part. Okay, the first part is just simply, here they carry it out to gory detail, and that would be the integral of y from 0 to 1 pi times pi plus pi times the integral of 2y, as you just said, minus y squared over 2. And this just gives you pi, which we could have gotten just looking at it. And then this would be pi times 4 minus 2 plus 1/2. The first three there add up to 0, and that just gives you half a pi, which is enough for right now. And 1/2 pi plus 2/2 pi is 3/2 pi. All right. Any questions on that? Basically the same way we did, except they went through a lot more work doing this and that, rather than just saying, hey, the volume of a disk is pi r squared times the h. The r is 1, the h is 1, so you just got pi. That works the same way. Notice that the first integral represents the volume of a right circular cylinder of radius 1 and height 1. Hey, yes, okay. You could have just done that from knowledge, okay. That portion of the volume could have been determined without using calculus, which is what we did, okay. Whoa, and that's all they write about it. So that's example 4. Now, they move on to solids with known cross-sectional areas, like we just did with that disk. They skipping example 5, which is an interesting problem. And I wish they had done it just to draw this diagram for me, because it's a pain in the neck to draw. So let's go to our whiteboard, and in this case I've got to move some stuff around. Here is my taskbar for the whiteboard, which is in the way, and then we've got the whiteboard itself is behind my picture, your names, that kind of stuff. And we still haven't heard from Ashton, have we? Has anyone heard from Ashton? He may have sent an email. I'm way behind on emails. I was out of town all weekend and we had zero internet for just about the entire weekend. It went out on us Friday evening sometime, and didn't come back till Sunday evening sometime. And we got there Friday and left early Monday morning. So we had almost no time with internet, and that what little time we had, it was very, very slow, and it was almost like both of us couldn't be on it at the same time or it would bog it down so slow. It was pathetic. All right. So I'm behind on emails. I don't know. He may have sent one. I don't know. The good news on example 5 is it is located at larsoncalculus.com. If you go there, you can see an interactive version of this type of an example. And this is a manufacturing type example. A manufacturer drills a hole through the center of a metal sphere. Okay? Now, I don't want to draw this. I probably will wind up drawing it. It's probably going to be so ugly we're not going to be able to see it. So I'm going to show it to you in the book. If you got your books, you already can see it. There is what we're talking about. There was a metal sphere, and he drilled a hole in it. And you see where he drilled the hole on the right hand side, but on the left hand side, the way it's turned, you can hardly see that, but the hole comes through back there as well. Okay, so he drilled part of the sphere in front and back. The hole goes all the way through. Okay, now that metal sphere, and he drills the hole through the center of that sphere, and the sphere had a radius of 5 inches. So I'm going to try to draw that, and you'll be laughing hysterically at my pathetic efforts, but let's see if we can get that drawn. I'm first going to draw the entire sphere here, try to anyway. So here will be my rendition of a sphere. Just picture that as having a radius that goes like this and also like this. Okay, that would be, that's getting uglier all the time. But then we're going to take it and drill a hole through it. Now this radius here, from the center of the sphere to any outer part of the sphere, is, let's see, what symbol do they use for it? I'm going to call it R sub s, the radius of the sphere. That's not going to be any one of the radii we're using otherwise, but this is equal to 5. Is it inches? Yeah, inches. Okay, 5-inch radius of a sphere. Okay. Manufacturer drills a hole through the center of a metal sphere of radius 5 inches, is shown in the figure, in my drawing. The hole has a radius of 3 inches. So here comes the hole that he's drilling, and it has a radius of 3 inches. Okay, and it's on the back side here. So he's drilling through here, this radius here, so the radius of the hole is 3 inches. Okay, so it goes all the way through the sphere like this. Okay, hope you sort of got a picture of it now. Ugly though it is, that's the picture of the sphere. Okay, now let's just put the axes, and they do this in the book too, through the center of the sphere. So there's the y-axis here, up and down. The x-axis goes straight through that hole. So there's the x-axis, right and left. Okay? So please say you want to do a dx. dy's would be horrendous. So we're going to do a dx here. So what we're going to do, okay, and this is going to be legal, okay, in most states, okay, we're going to do what this would produce then, that dx there, if you cut through the thing, would then be also over here. And this goes all the way around, so you would have a thing that goes all the way around like that, and that's your slice. Okay? Outer radius, inner radius. But the slice is from here, not here, so that radius is different. Okay? You're going from the x value to here. So we sort of need to get the equation for that sphere. And here's what it is. The let's see how to say this. The formula for the volume of a sphere, which is not really what we're doing here, and by the way, there, I'm starting to do it this way too, but if you, well, no. I was going to say it would almost be easier to just take the volume of a sphere and subtract from it the volume of the cylinder, except the cylinder isn't flat on the ends, it's curved on the ends. So we still have a problem there. So what we're going to try to do is do the volume of that little disc that a washer that you have there, and every one. Okay, so what we need is this radius here for that washer there. Okay, now this is a different radius from either the sphere or this one. This is our outer radius, and that radius we're going to call, like the book does, I think, capital R. Okay, now I do want to point this out to you. This length here is your x, right? This length here is your 5, radius of the sphere. So this radius here is the square root of 25 minus x squared. Yuck! It'll go away, I hope. Okay, there it goes. I don't know if y'all could see that or not. So this radius, I know it's an ugly picture so far, but this disc here is centered on the x-axis. You're this far out the x-axis, and you're going up here. This part of that triangle is 5, this part is x, so this length here is the square root of and that took away part of my x, didn't it? 25 minus x squared. That's your outer radius. Your inner radius, you know what that is. The inner radius, this is the inner radius here, and this is our little r. Okay, I said that wouldn't be either one. It really is. That's your inner radius of that. Okay. Now, the one other thing we have to deal with is what the limit on x is, because you're not going out to 5. You cut away that part. You're going to here. So what is the x value here when the y here, yuck. Okay. When the y is 3, what is the x value here? Well, you know this is still 5. So now the x, the maximum x is going to be, I'm going to call it x max, is going to be the square root of 25 minus 9, which of course is 4. 25 minus 9 is 16, square root of 16 is 4. So our x is going from, now here's where I'm going to cheat some, 0 to 4. But wait a minute, don't you have a sphere over here? Yes, but that's completely equivalent to the front side. So we're going to do our integral then, the volume, is going to be twice pi. You got the pi in there because it's pi r squared, you know, the pi is there, the integral, and the dx, that's going to be our increment. Okay, the dx, it's going from 0 to 4. Now you could have done minus 4 to 4. Why go to that effort? Just do 0 to 4 and double it, because that's totally symmetric. And then what is your outer radius? That would be 25 minus x squared, the square root of 25 minus, so that would be 25 minus x squared minus, and remember the inner radius is 3, and 3 squared is 9. Okay, well, we can clean that up just a little bit. That would be 2 pi times the integral from 0 to 4 of 25 minus 9 is 16. We've already determined that, minus x squared dx. The setup is the hard part. The calculus is the easy part. 2 pi, relatively so. What's the antiderivative of 16? Anybody? 16x minus antiderivative of x cubed. I mean x squared. I'm already saying it for you. Antiderivative of x cubed over 3. See, I was already answering the question, and you're doing this from 0 to 4. All right, so what do we have? 2 pi, easy part, times 16 times 4 is 64, minus 4 cubed is 64 over 3, so that would be 64 over 3, and but 0 is going to give you nothing, so that's what you got. Well, let's make this 3 times 64 over 3 minus 64 over 3, and that would give us 2 pi times 2 times 64 over 3. Well, 4 times 64, which is basically what we've got there, would be 256, I believe it is. So that gives us 256 pi. I'm going to try to write it like the book does. Watch them change now. Over 3. Let's see what they got. 256 pi over 3, and I, of course, ashamedly left off my units, and these are cubic inches, because everything was measured in inches before. So 256 pi over 3 cubic inches, which is just a tad more than 256. Probably more than 260, maybe even close to 270. I don't think they round. Oh, no, they don't. Because you see, pi is very close to 3, just a little bit more than 3. So you're just multiplying 256 by a number just a little bit greater than 1. Okay, so somewhere between 260 and 270 cubic inches is what I would guess, but I'm not going to worry with it. Okay. Now, they did it minus 4 to 4 rather than doubling in 0 to 4. You see, we got the same answer with a lot less work. All right. Any questions on that one? Okay. Let's go back to the PowerPoint, which is 7.2. So this is it here. And I may have to go clear my head. I hate to do that, but I forgot to check and see what the time was. 10:48. And we go to 11:40. So I've still got almost an hour to go. I think I'm going to have to go clear my head. So do you mind if we take Uh, we're going to start that. Let's do a quick pause. Let me run, clear my head because I'm getting so congested I can hardly talk. So I'm going to stop the recording for right now. Any questions before I do this? I don't want you to have to sit on a question for a long time. None? Okay, why don't y'all take you a quick, oh, does someone have a question?
I'll stand on it.
Okay. So if y'all need to take a break, take one quickly. If you happen to hear that Ashton is trying to get in, tell him I'll be right back. But I have to go clear my head because I am so congested I can hardly breathe. So hold on. Let me pause the recording. Don't see anyone trying to get in, so we'll assume not. Okay. So now we're on page 459, bottom half of the page, solids with known cross sections. Okay. It's a strange sounding title. Okay, well, I gotta click the screen before it'll advance. With the disk method, you can find the volume of a solid having circular cross section areas, and the area is pi r squared. That method can be generalized to solids of any shape. They don't have to be disk anymore, as long as you know a formula for the area of that arbitrary cross section. Now, some of those common cross sections would be squares. We know the area of a square. Rectangles, you've been using that all along, areas of rectangles. Triangles, you know the area of those. Semicircles, as well as circles, these are circles here. And even trapezoids, okay? I have to refresh your mind on the area of a trapezoid, but that should be able to go with it. So, sorry, I still can't breathe. Volumes of solids with known cross section for cross sections of some area A of x, that you know the area, taken perpendicular to the x-axis, okay? The volume would then be the integral from little a to little b of that area of that cross section times dx, okay? Now, oh, okay, I had my axes crossed up. Here's the axis here, there's the y-axis here. Now they say, what if you know the area of a cross section? And you're doing dx's, okay? This is not a known area here, okay? That is a length here, but this length here is not the same as that one over there, and this is a curved length here, certainly not the same as the length down here. There would be a cross section perpendicular to the x-axis, but we don't know the area of that cross section. However, that same thing, if we took the cross section with the y-axis, now you look at that, do a dy here, and your length down here is the same, or at least it appears to be the same as the length up here. Not knowing the formula, it's hard to say. And certainly the length here is the same as the length there. There's a rectangle. We know the area of this rectangle, so do your dy's here and then go from 0 to d. That would be your known using a known cross-sectional area. Okay? This is not a known cross-sectional area. If you knew that area, A of x, and maybe you could figure it out. If you knew that the shape of that curve there, yeah, that may be something you could figure out. So that volume would then be, and as long as it's the same coming this way as it is that way, you could actually do twice 0 to whatever your b is, rather than going from A to B. But you could always do A to B if you knew the area of that cross section or could calculate it. This one would be even a little easier. This would be 0 to D with dy's. Okay, they say y is equal to c back here, but I can tell that if that's the x-axis, that's from 0 to D. Okay, if you know that cross-sectional area. Sometimes you will, sometimes you might have to calculate it, but that's the setup for the procedure we're going to follow now. So here comes example 6. Okay. Find the volume of the solid shown in figure 725. That's this one right here. The base of the solid is the region bounded, the base down here, this down here, going from -1 on, now they turned it around on it. This is y, -1 on y, +2 on x, to +1 on y, and then back to -1 on y. Okay? So the base of the solid is a region bounded by the lines. This line here would be, if you think about that, kind of take this, it's hard to read, take that triangle and flip it up like this and make it XY thing, then this would be the line. You'd have a slope of -1 here, no, -1/2 here. Okay, you're going from 0, 1 to 2, 0. Okay, that line would have a slope of -1/2 and a y-intercept of 1, so that would be -1/2 x plus 1. And there it is. They wrote it in a different thing. That's their G. Okay? No. This is their F. -1/2 x plus 1. They wrote it in a different way. Not sure why. It made it hard. This one down here, the g of x, that has a positive slope, and that's a positive 1/2 slope there. And your y-intercept is -1, so it would be 1/2 x squared, 1/2 x minus 1. And that's what you have here, -1/2 x minus 1. Now you might ask yourself, why do you need to know those two equations of a line? Okay, of those two lines. Well, what we're going to do is use the difference between those two lines, f of x minus g of x. Okay, that's going to be the length of your base of that triangle, and then the height of the triangle you're going to have to get from elsewhere. Okay, so and we're going to talk about that. Now they don't show here. Okay, right, okay. The cross-sectional perpendicular to the x-axis are equilateral triangles. So we do know those. Okay, I hadn't read that part yet. I was going to say that looks like an equilateral triangle here, but they didn't tell us. Not up here. I was looking up here. Down here they did tell us. The cross-sectionals perpendicular to the x-axis are your equilateral triangles. So you have your dx, you have y as a function of x here, 1 minus x over 2. You have y as a function of x here, -1 plus x over 2. Okay, the way they've written it. And then all you need, okay, here's the other thing. They're kind of leaving out for you, but I want to draw it in. I don't know if they're going to do it this way or not, but if you have an equilateral triangle, okay, that's the base. That's going to be our f minus g. Okay, if that is indeed an equilateral triangle, then this is a 60-degree angle, this is a 60-degree angle, and that was a 60-degree angle, but then I put the bisector in it, and that makes each of these 30 degrees. Okay, 30 there and 30 here, which is 60 degrees. If you know the base, the height here is going to be half the base, okay, times the square root of 3. Because, okay, a 30, 60, 90 triangle, if you remember from trig, the sine of 30 is 1/2, 0.5, okay? Or think of it this way. If this was 1, that was 2, this would be square root of 3 here, okay? So it's half the base times the square root of 3. That's going to be your height. So you know the area of the triangle is the base times 1/2 of the base times the square root of 3. So the area of that triangle is going to be, and this is the equilateral triangle, is going to be 1/2 the 1/2 times the square root of 3 times the base squared. Because it's the base times square root of 3 times the base. I left out another half. I think this is going to be over 4. Okay, because this height here is 1/2 of the base times the square root of 3, and then the base, and the formula for the triangle is 1/2. So that gives you 1/2. So it'd be, what this comes out to be is the square root of 3 over 4 times the length of the base. What's the length of the base? Length of the base squared is the difference between this and that. Okay? So, let's do that. F minus G is going to be 1 minus x over 2 minus x over 2 plus 1, because of minus a minus. Okay? So that gives you 2 minus x. That's going to be the length of the base. Okay? That's pretty amazing, isn't it? And of you wouldn't think it would be that simple. But when x is 0, certainly that length is going to be 2. And when x is 2, that length is going to be 0. So, yep, that looks like it. Okay? So, I think we have what we need. This is what I've been calling, where is my pen? Here it is. This is also what I've been calling the base. So that's what we're going to put in there. All right. Now, let's see how they proceed from here. Well, let's see how we're going to proceed. So what we would have would be the integral. You're doing your dx, so that's going to go from 0 to 2 of, and you're going to have this the square root of 3 over 4 out front from here. And then you're going to have this thing squared, which is 4 minus 4x plus x squared. I squared that base, and that square the first term, twice the product of the two, square the last term, squared. I didn't write my x squared in there. And then dx. All right. So let's see what this gives us. Root 3 over 4 times the integral. What's the antiderivative of 4? For x minus, and this will be x squared over 2 times 4, 2x squared, minus x cubed over 3, and we're evaluating that from 0 to 2. So this will be square root of 3 over 4 times, when you plug in a 2 there, that 2. That gives you 8 minus, and 2 squared is 4 times 2 is 8 again. Well, that's going to be pretty easy. Minus, whoa, you can't come up with a negative. I've done something wrong here. I can't see where it is. Oh, that isn't a minus, that's a plus. Okay. Whew. Okay. Good deal. Okay. 2 cubed is 8, so it's 8 thirds. Okay. And then the zeros give you absolutely nothing. And then the 4 will go into 8 twice. And this is a plus here now. So you have 2 root 3 over 3. At least that's what I get. Now, I was doing that awfully fast in my, oh, and yes, that's what the book got as well. 2 root 3 over 3. Let's see how they did it. Maybe they'll make more sense than I will. Okay, the base and area of each triangular cross section are as follows. The base is the difference between those two, which was the 2 minus x, exactly what we called. I called that little b. Okay, yes. Now the area, and they just came up with, they didn't show you why, but they came up with the square root of 3 over 4 times the base squared. Now, I tried to show you why that's true. Hopefully what I said makes more sense than just writing it down like that. That's not a formula or function I would never normally know. You have to figure it out, but that's what we got. Okay? And this base is this thing right here. This base here is that thing here. So that's going to be the a of x is then root 3 over 4 times 2 minus x squared. And of course we're going to take the volume to be the integral from a to b, which for us is 0 to 2, of your a of x, which I just wrote down here, which I'll pull the root 3 over 4 on the outside, square that binomial, and that's what's on the inside, times dx. So that gives you the integral from 0 to 2, and they left the root 3 over 4 inside. They'll pull it out in a minute, this squared. So let's see what they do. Yeah, they pull that on the outside. Now, okay, they did their integration differently, and it's perfectly okay to do this. To me, this opens more opportunity for error, but it is perfectly correct. The antiderivative of 2 minus x squared would be 2 minus x cubed times the antiderivative of the inside, basically, which is a minus 1. That's where the minus comes from. If you do the sort of the inverse chain rule, I can't think of anything better to call it, of this, you get this thing here cubed over 3. That's where they got theirs. And then because you have this is a minus x here, you have to do a minus out front. Now, I sure wouldn't have done it that way, but it's perfectly legal. And if you do that now, what you get is when you put a 2 in here, that goes to 0. So now the upper limit is a 0. Put a 0 in there, and you get 8 thirds, which is exactly what we got. But because you're evaluating from the lower limit, that's going to be minus this. So there goes your minus sign away, and it's root 3 over 4 times 8 thirds. Okay? 4 will go into 8 twice, and you get 2 root 3 over 3. Exactly like we got, but gone about kind of a different way, especially doing the integration. That was totally bizarre in my mind to do it that way. Just so much easier to square that binomial and integrate like we did. Okay, but you get the same answer. As long as your steps are correct, you should get the right answer. Now, I'm guessing that may be the last slide in the set. Let's see. Yes, it is. So we're going to have to go back to the whiteboard. And let me do that if I can do it down here and go back to the whiteboard. And let's clear that out of the way. Clear our drawings there. And this is, well, it's okay. Let's do example 7. Prove that the volume of a pyramid with a square base is V is equal to 1/3 height times the base. Now, they telling us that is the answer. They want us to prove it. Now, H is the height of the pyramid, and B is the area of the base of the pyramid. Okay, so they're going to make me draw a pyramid. Now, I'm going to show you how it's supposed to look, and you're going to have to use your imagination. There's a pyramid, square base, and they put the center of that base right through the center is the y-axis. Okay, so your length that you're going out x is 1/2 that base. The dimension of that square at the bottom, and your y's are 2. So there it is, and it's going up to some height there. Okay, H we have no knowledge of at all. Okay, now as you may have noticed when you looked at that, they did the cross-sectional areas dy's, okay, because they had the y going out of the top. Okay, now that makes the area of an increment there smaller bases. At the bottom it's that regular base, and then you're going up and they're all squares. Okay, now the problem is we've got to get our dimensions worked out. Okay, now let me again write for you what I'm going to try to draw. I'm going to try to draw, if I can get my pen to show up somewhere. There it is. Okay, this figure, and this is going to be laughable. Okay, there's going to be the back edge. There's going to be sort of the other back edge. This is going to be this edge and that edge. That's your square base. Okay, now they label that, and here's your origin right here, and they don't put a cross section here, but they put the x's going this way. So this is your x-axis here, and your y-axis going straight up from there. Okay, now here's your pyramid. Ugly as it is, I never can draw them that the one side isn't going to interfere with that. That's supposed to be the pyramid. Now somewhere up here we have a dy, so let's just do a dy here, and that dy is going to translate to be a, these are not showing up well at all. Okay, yuck. Okay, I don't know what that did somewhere, but anyway, this is going to be a plate here, 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 and here of thickness dy. So it has a little thickness here, and it's going here, 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 and there. Sorry, something like that. Now, and that's the square base. This down here they're calling, this length here is the little b. The height here from along the y, okay, is going to be going to h. So y is going to be going from 0 to h. So this height up here is y is equal to h. And that's the height of our pyramid. So we got that done. The little b down here will be such that b squared is equal to what they called the volume of the base. I mean the area of the base. Okay. Now we're not there yet, so hang on to that. But remember, that is that. If that length at the base is, and that's a B, that's a B, this is a B back here, that's a B here. Okay, now let's find out for this rectangle I've drawn here, somewhere up the y-axis, there is your x. Okay, the y is going to be this length here. Yuck! Is the height of this. That's your y. Okay. Now, let's take, if I could get my pen to move, here we go. From the height here, the peak there down to here, that is a slant height here. And what's left over here is h minus y, because y is the height from the origin up to here, so this is going to be h minus y here. So that forms you a triangle. One leg is going to be h minus y, the other leg is going to be x. Okay? Now, what good is that? It's got to be of some good here. Okay? You need to get x as a function of y so you can plug in, because you're doing dy's here. So you need the area, okay, this is x, 2x is going to be the length of that, and that will be the same here. This will be 2x here too. Okay, so this base has an area of 2x squared. Okay, that is a of x, but we need that to be an a of y. Sorry. Okay, now what we need is to find this x as a function of y. And we know this is h minus y here, and this is x here. And I think you just use Pythagorean theorem here, but let me check and make sure. Okay. Okay, this is where you get this triangle that I've drawn right here that's sort of messy in here. X is that dimension, h minus y is that dimension. Okay, that triangle is similar to the one down here, and the one at the bottom here is b over 2, and that's your h here. So what we are trying to do is to get, these are similar triangles. Okay, so your x over h minus y, that would be this length over that length, is the same ratio as b over 2 is to h. Okay, because on the base here, your x is b over 2 here, and your height here is h. Okay, now just to make things a little easier, I'm going to multiply everything by 2. And this would be 2 x over 2 times h minus y is equal to b over 2h. Okay, that just gets rid of those denominators because they were kind of messy. And we're wanting to solve this for x. So what we have here is 2, make that 4xh, when you multiply those two together, is equal to 2b times h minus y. Okay, so solve this for x, and you have x is equal to, well, let's factor out a 2 and have b times h minus y over 2h, sorry, 2h. Forgot about the h there. Okay, now remember our area? I wrote it down somewhere here. The area of this was 2x squared. So we actually want 2x. So I shouldn't have ever divided. I want a 2 there. And that would have just been divided by h. Okay. So that's what we have. So 2h squared would then be 2x squared would then be b squared over h squared times h squared minus 2hy plus y squared, squaring that binomial. Okay, that's your area. Okay, so that's the area of that rectangle, that square that's in there. So what we're going to do now is do the total volume is going to be the integral from 0 to h of, and this b and h are all fixed here, so that's going, and by the way, that b squared is your capital B. So let's just replace that with capital B here over h, right? Because b squared is b, and this will be b squared, which is, so that's over h squared. That's b squared over h squared, so that would be capital B over h, and then what we have here, integrating h squared minus 2hy plus y squared times dy. The dy gives you your thickness, that's your area. So let's see what we got. We got a capital B over h squared. Okay, and you're going 0 to h here, those are your limits. Well, h squared is a constant, so that would just be h squared y minus, and this will be y squared over 2, well, that will wipe that out, that would be h y squared minus, plus y cubed, if I could get my pen to write, y cubed over 3, evaluative from 0 to h. Okay, so what do we have? We have the b over h squared here times, when you plug in an h for y, this gives you an h cubed minus an h cubed. I can take care of those. Those add to 0 plus h cubed over 3. Well, those added to 0. This h squared down here will divide into that h times, and what do you get as your answer? 1/3 the base times the height, which is exactly what they told us the formula was to begin with. They put the h in front. The volume is 1/3 the height times the base. That's exactly what we found it to be. Whew. All right, that finished 7.2. Any questions on that one? I know that's sort of messy drawing. That's why I wish like crazy they would have given me at least the drawing. Let me do the math, but do the drawing for me, because that's really ugly. But I hope you followed what we were doing there. All right, any questions? Well, that finishes. Let me make sure Ashton's not out there waiting. I sure didn't see him show up. Nope. Okay. It finishes 7.2. Homework exercise here. Now, always do the concept check. I don't usually say it out loud, but always do the concept check. That just reviews for you it basically is a summary of the concepts that section is dealt with. So do that. Homework exercises then would be either 5 or 7. They're both at Calc Chat. 5's at Calc View. 9 or 11. They're both at Calc Chat. 9's at Calc View. 13 or 15. They're both at Calc Chat. 13's at Calc View. 17 or 19. They're both at Calc Chat. 17's at Calc View. 21 or 23. They're both at Calc Chat. 23's at Calc View. Any of the odds 25 to 31, this is on page 462, the previous ones were on 461. Any of the odds 25 to 31, they're all at Calc Chat. 33 or 35 are both at Calc Chat. 37 or 39 are both at Calc Chat, with 37 being at Calc View. Any of the odds 41 to 47, they're all at Calc Chat. 49 or 51, they're both at Calc Chat. Now they say you may need a graphing calculator or utility for that. I think you can probably do it. If not, and you don't have one, don't sweat it. You can explore doing 53. It should be at Calc Chat. 55 should be at Calc Chat. 57 should be at Calc Chat. Then you can choose to do any of the odds 59 to 69. They should all be at Calc. Well, let's see, more than that. 59 through 75. And they should all be at Calc Chat. Now, pausing a moment here. I just saw one. I was just trying to make sure there were others. Number 72 you don't have to do, but take a look at it. Cavalieri, or I don't know, Cavalieri theorem. Who in the world was Cavalieri? Okay, how did he come up with that theorem? What's the practical uses of the theorem? Any of those kind of questions could be potentially good paper topics. Hint, hint. I think I've only received maybe one paper from this class, and we only, today's the last day to get your 3 bonus points. Next month it's only going to be 2 bonus points. Okay, so get me your papers if you haven't gotten them already. All right, the rest of that, there's another for further information. They reference the journal article. You can use that article to be your source or one of your sources of a paper. So please don't forget about your paper. Okay, any questions on 7.2? All right, we got about 9 minutes left. Let's move on to 7.3. So I'm going to go back to our slides, which we were through with, and go to 7.3. Let's see if that's it here. No, that's 7.2. That's 7.2. It was up here earlier, and now it's, here we go. Is this it? I don't think so, but I'll get it up this way. All right. Now let's do a new share on that one. Yeah, here we go. All right. Let me get from current slide. All right. We're still in Chapter 7, Applications of Integration. 7.1, area between two curves. 7.2, volume of shapes that are rotational around the curves rotated around an axis by the disk method. 7.3 is going to be talking about calculating a volume by the shell method. Sometimes disks are either inappropriate or impossible to do by way of a disk, or if not impossible, way too hard. Okay, so we'll see an alternate method called the shell method. Now the objectives are to find the volume of a solid of revolution using the shell method, and the second would be compare the uses of the disk method with the shell method. You'll see sometimes disk is way easier, sometimes shell avoids a lot of problems. Okay, so you can use either one. So what in the world is the shell method? Now I really don't care too much for their approach here. It's okay, but it's a lot of words and it seems like it could be made simpler. An alternative method for finding the volume of a solid of revolution is called the shell method because it uses cylindrical shells. A comparison of the advantages of the shell disk and the shell method is given basically toward the end of the section. Let's consider a representative rectangle, and that's this one right here, this one that's sort of a pinkish color, and you see its length here is from the H here. That's what the length of that rectangle is. The width of the rectangle is that W right there. Okay, so the length by width is the area of that rectangle. Now what are we going to do with that rectangle? We're going to revolve that rectangle around your axis of revolution. Okay, now if you think back on it, the disk method, the W was always along the axis of revolution. Now your W is perpendicular. So this is one big difference here. Your incremental thing is now perpendicular to the axis of revolution, not parallel to it. Okay, so that's going to be an issue. Now, how do we get the volume of that shell that's formed there? Well, the cross-sectional area is W times H. Okay, the length of that, now here's what I want you to imagine. Let's imagine you had some scissors and could cut, or maybe shears or something, you could cut that shell in two right there, just straight along that thing, and then flatten it out. Okay, what would you have? You would have a rectangle. The width of that rectangle would be your H here. The length of that rectangle would be the circumference of that circle. Now, they go into all kinds of gory detail about talking about P plus W over 2 is a longer length and P minus W over 2 is a shorter length, where P is, yuck! I just lost Zoom. I just got Zoom back. I know I must have broken up in there. Zoom just died on me and then it came back. And I don't know what it brought up in the background. I'll worry about that later. But y'all can hear me now? Can you?
Yes, sir.
Okay, good. Let me get my PowerPoint back up. It just lost it completely. And we'll go from current slide. We lost everything. Okay, let's go back to this shell method. Okay, and you can see my slide there, right? let's go from current slide then. Yep, this is where we were. And let me see if I can get this taskbar out of the way because it's smack covering what I wanted to talk about. Okay. They go into gory detail about the P plus W plus 2 and P plus minus W plus 2, where P is the average thickness of that thing. In reality, that's all we're going to use. The difference between P minus W plus 2 over 2 and P plus W over 2 is negligible. So forget about it. Just use P. So P is the radius of your rotation there around that axis. Okay? It's the average. Okay? And that's going to be 2 pi times that radius. That's going to be the circumference. The circumference of this, the length here going around here, around there, around there. So if you flatten that out, that would be the length of the rectangle, 2p 2 pi p, 2 pi r. So 2 pi p times the width times the thickness. There's your volume. Now they introduce this P plus W over 2 and P minus W over 2. They go through all this and then later ignore it. Okay, so why mess with it? Okay, and P is the distance between the axis of rotation and the center of the rectangle. That's all that's going to matter. Okay, now 1 minute. When that rectangle is revolved around the axis of rotation, it forms a cylindrical shell or a tube of thickness W. To find the volume of that shell, consider the two cylinders. They do the inner and the outer. Don't worry about those, okay? The outer radius is this, the inner radius is this. They go through all this stuff and then say, look, they don't really matter. Just use the P. Okay, so what have we got? 2 pi p, that's the circumference of that shell, times h, that's the length of the shell, times w, that's the thickness of the shell. There you have it. Length times width times thickness. Okay, 2 pi p is the length of that shell when you flatten it out. H is the width of the shell, and w is the thickness of the shell. So it's 2 pi times the average radius, P, times the height, times the thickness. That formula used to find the volume of revolution. Okay. Now, I bet you we're out of time. Yes, we are. So, let's see where we're going to pick up next time. It says, for instance, let's see if I can find that for instance here. I can't. Okay. Yes, there it is right there. All right, we'll begin on page 465. We didn't get enough covered in 7.3 to do any additional homework problems, so that where we are, 7.2 will give you plenty to work on, plus your research paper, plus everything. So please have a good weekend, and of course working on Cal 3 will make it Cal 2 will make it a good weekend, right? Yes. Any questions?
No, I got a question to ask you.
Surely. Okay. Okay, now you want to wait till the others sign off, or you want to contact me some other way?
Wait till the other sign off.
Okay. Do the other two of you mind signing off? I'm going to stop the sharing now.
I'll see you later.
Okay, take care, Brandon. And Andy just banked out. Okay, it's just the two of us now. You want me to turn off the recorder?
Yes, sir.